this is a permutation. Let me just show you. Okay. That's what you call a permutation. Okay.
Oh my goodness.
What is that supposed to be?
I don't know. It's a mutant cat. No. I just found that on the internet to make a joke. Okay. So this is 8-5, okay, and this is, am I recording? Oh, I recorded that. So 8-5, this is called the counting principle. Counting principle, okay? And what the counting principle, I think it's LE, right, says is that, I guess I have to write this out. If, I guess I'm going to write it with my, maybe I'll write it with my keyboard because that's faster. Should I? Text. Keyboard? Does this do text? No. I'm going to do it like this. If. No, never mind. I'll just write it. Take it, because I have to use sub thing. Oh, sorry.
Not that.
So the counting principle says this, that, go away, I want to get this, there we go. It says if you take, no, that's wrong. If E sub 1, I can't write very well with this. And I like writing on the board better. E sub 2 are two events. And E sub 1 can occur in M sub 1 ways, okay? And E sub 2 can occur in N sub 2 ways. Then the number of ways that both things can occur both, I always write both, I must with an E, I must be from England. Both events can occur, and you kind of already know this already, but is M sub 1 times M sub 2. For instance, if you flip a coin and roll a dice, how many things could happen? How many things could happen if you flip a coin? Two things. How many things could happen if you roll a dice? Six. So altogether, there's 12 different things that could happen. That's all that's saying. Okay? So all you do is you multiply. If you have the other instance, like if you have 3 shirts and 6 pairs of pants, how many different outfits could you have? 18, right? You multiply them together to get the number of them. So what if? So if you not flip a coin, roll a dice. Roll a dice. Twice. Roll a dice. Is it roll a dice or roll a die?
Roll a die.
Roll a die.
Just
roll a die.
Roll
Roll a dice twice. Roll a die twice. Oh. Roll a die.
Roll the dice twice.
You don't roll it. Roll a die twice. Then how many ways? How many ways are there? Are there to get an 8? 8.
Oh, like combined.
Yeah, how many different ways are there to get an 8? What?
There's like a lot of
What's one way to get an 8?
2 plus
2 and a 6.
2, 4, 4.
Or I could get a 6 and a 2 is different than rolling a 2 and a 6, right?
4, 4, 4, 4.
Okay, you could get a 4 and a 4.
No, 7.
And you could get a what and a what?
4 and 4.
No, you can only get a 4 and a 4 one way, right?
8 and 0.
And a 5 and a 3. How many different ways are there?
5.
7 and 1.
1, 2, no, you can't get a 7. You can't get 7 if you're rolling. I've done that too, don't worry. Yeah. Okay, so altogether there's 5 ways out of the total, which is how many different events could occur when you roll 2 dice? 36.
Oh, 30, wait,
Right?
time out. Isn't there only 35?
No.
Because 4 and 4 is the
What
same.
is 6 times 6, Brian?
6 times 6 is 36.
I know, but
No, but if you get like a 1 and a 1 and a 2 and 2, that can't happen
Yeah.
2 separate ways.
I know.
Well, the order is
No,
different with the 2 dice.
Well,
oh,
it
wouldn't there be like 2 types of?
All you have to do
4 and
is multiply it.
Yeah, no,
Oh,
it's
yeah.
not
That
a
easy.
good point.
You're overthinking it.
yeah, all you have to do really is.
Shouldn't there be 2 4 and 4s?
All you really have to do is make a table, okay? So if you were to make a table, can I make a table? I can make
Oh,
a
I
table,
get it.
right? And you could put lines on the table and go divide it into 6 pieces, right? 1, 2, 3, 1, 2, 3, 4, 5, 6, 1. I should have done it. And 1, 2, 3, 4, 5, 6. Do you see that 36 different things could happen?
Yeah.
Alright, this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep. And you could add them all up. That's the way you calculate that. Okay. So there are only 5 out of 36, but we're not really doing probability, although it is interesting. So really what a permutation is, okay, this is what it's not a cat, that looks funny, okay? A permutation is an ordered arrangement, an ordered set of n different elements. Ordered set of n different elements. Okay? So for example, how many different arrangements, if I were to arrange 4 books on a shelf, 4 books on a shelf, how many different arrangements could I put those 4 books into? How many choices do I have for the first book? 4. How many for the second book? Not 4. They have
11.
3. How many did I have that for the second arrangement? 2. For the third book, I have 1. The other way you can think about it, like I have 4 books. So maybe we have book A, we have book B, we have book C, and we have book D, right? So if I choose book B to be first, then I have 3 choices for the second book, right? So the second book I could pick either B, C, or D, right? If I choose book B to be first on the shelf, then I could choose A, C, or D, right? And so on and so forth. If I chose A, then B, how many choices do I have for my third book in the line? 2, right? I can only choose C and D. And if I chose this path, A, B, and C, what would have to be left? D. And if I went A, B, D, then I'd have to choose C. So altogether, there's 4 times 3 times 2 for each of those choices times 1 for the last one. You get it? Yeah? So that's where the 4 times 3 times 2 times 1 comes from. What if I had 10 books and I wanted to put, how many choices would I have to align 10 books on a shelf?
10 exclamation points.
10, no, it's not 10 exclamation. If I only had 4 spots to put them, how many choices would I have? 10 times, not 10 times 4. It would be 10 times 9 times 8 times 7, right? You have 10 choices for this book, 9 for this, 8 for this, 7 for this. That's known as 10 permutation 4, okay? And so a permutation NPR, National Public Radio, okay? That's equal to n factorial. Your parents probably listen to that. Over n minus r factorial. That's how you compute a permutation. So for instance, this one up here, think of it this way. It's 10 times 9 times 8 times 7 times 6 factorial divided by n minus r factorial. What's 10 minus 4? 6 factorial. And then you just end up getting this same thing, you see? So using the formula, you get this. Using just kind of the counting principle, you would get this. Follow that?
Yeah.
Hey, wake up, Hunter. You understand that? Hello, guys. So, what if you're playing baseball? You want to know how many different baseball? How many? What? Can I go back? Uh-oh. Are you okay?
Yeah, I was just
Okay. Can I go forward now?
Yeah.
How many different, you have to kind of be baseball literate, okay? Batting orders. Permutations we talked about, and probabilities we talked about this kind of stuff. How many different batting orders are there on a team of 15 players? Do you guys know do you know about baseball club?
Yeah.
Do you know how many players, do you know how many players on a baseball team? You know, who can tell Chloe how many?
You play with
Field?
Yeah, on the field at one time.
None.
So altogether, when you play baseball, there's an order, right? First guy goes first, second guy goes second. So you have 9 players, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. If I have 15 players, how many choices do I have for this spot? 15. Then 14. Then 13. Then I go all the way until I get to whatever comes at the end. What would that be? Would that be 6? I think it'd be 7, right? 7, 8, 9, 10. Yep, it'll be 7. Because this is nothing more than 15 permutation 9, okay? Which is that's not a Q, that's a 9. Sorry. I don't. That now it's like a G. It was better the first. 15 permutation 9, which can be written as 15 factorial over 15 minus 9 factorial, right? Which is just 15, which is just this, right? And if I did that on a calculator, I get a giant number. You get 1 billion. You get 1 billion. 1,816,000. 816 million, sorry. 214,000 and 400 different batting orders you could have if you had 15 players. How about that? You know, when your coach does the swim relays, right? Hey, I want to be first. I want to be second. And he has a whole lot of time. How many swimmers do you have on the team? How many people are on your relay team?
4 in the relay.
Oh, how many different ways could you arrange those 4 in the relay?
Well, it depends on the swim.
Wow. Oh, everyone has a specific
There's
job.
a lot of people.
Oh, okay. Yeah, but the coach, like, you could change it up, right? 4 times 3 times 2 times 1 would be, there'd be 24 different ways you could arrange 4 people on a swim team. Okay. What about how many ways? I'm going to do another one. And this is how many distinguishable ways, distinguishable, yeah, distinguishable ways are there, and this is important, distinguishable ways are there to make words, actually 11 letter words, 11 letter words out of the letters in Mississippi. I'm getting good at spelling this now. Mississippi. Okay? That's 11 letters. How many different ways could I arrange those letters? 11. What? How many choices are there for the first spot? 11. There's 11 different letters, right? How many for the second spot? 10, right? So I had 11 times 10 times 9 times 8 times 7 times 6, blah, 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 until I get to 1. That would be 11 factorial on the top.
Well, they're not necessarily going to be words.
Right. Oh, yeah. We're considering a word to be any arrangement of letters. However, if they're distinguishable, could I tell if I had an I or an S here and an S here, could I tell the difference between those two S's? No, right? What? And if I had an S here, and if I had an S here.
So the
So,
S's can't go back there.
If I had to like call this S1, S2, S3, S4, S4, right? I could tell the difference, right? But since I can't tell the difference, I have to divide by how many different arrangements there are of 4 things. How many ways could I arrange 4 S's? 4 factorial, okay? So if I am doing this, if they say distinguishable, you need to divide by the number of repeats of the S's, and you need to divide by the number of repeats of P's and I's, okay? So if you did this out, you would get some number which isn't as big as the baseball player would, okay? You get that?
Yeah.
Most of you, okay? Because you have to divide by how many different ways could I arrange these repeats. Because 11 factorial accounts for all the different ways to arrange these letters, okay? So I could have S here, S here, S here, but the 4 factorial accounts for this S being here versus here and so on and so on. Okay, done with that? Yes, sir.
With the baseball player one, is there a way to do it like if one like thing had to be in the
Like one person had to be
Yeah.
cleanup or
or
something?
they had to like be in the lineup? Is that
If one person, well, they need, so if one person had to be in the lineup, right? They have, right, so say, I don't know, some guy has to, you can only choose one guy to be cleanup, right? Then, how many choices do I have for this? If there's 15 players on the team,
14.
then I have 14 times 13 times 12 times 11 times 10 times 9 times 8. So you'd have 1 times 14 permutation 8. You see? That's what's so confusing about probability, because sometimes, oh, maybe I have 2 players for this, right? So then it gets really confusing. Yes?
On that one, do you also have to divide by the n minus r factorial?
For this one?
Yeah.
Yeah, but n minus r is 1, right? N minus r, 11, this is 11 permutation 11,
Oh, yeah,
right?
yeah.
So it's 11 factorial over 11 minus, or over 11 minus 11 factorial, which is 0 factorial,
Okay.
which is 1, right?
Yeah.
And so that kind of helps math. So then we're going to talk about combination. We talked about combinations the other day, but combination order is important. We're going to do a fun problem in a minute. Just hold on. Combination order matters. Order doesn't matter. Okay? Order does not matter. So when they're talking about combinations, they talk about committees. Like how many different ways? Committee. How many different ways are there to arrange 5 people on a 3-person committee? Okay? 5, or they talk about card hands. We'll talk about that because it's kind of fun, but we're not going to get too into it. But 5 committees, 5 people, 3-person committees. Okay? and committees. And so that is 5 combination 3, which we learned the other day is 5 factorial over 5 minus 3 factorial, which is 2 factorial, but then you divide by 3 factorial, okay? Because what this is, so say you have 5 people, okay? We have person A, B, C, and D, and E, right? So how many people could I choose for this spot? 5, right? If I have 5 people, but I'm only 2, and it doesn't matter who is, which position these people are in. So I have 5 choices for this. How many choices do I have for this? 4. Once I've used up one of those people, I have 3 people over here. So that accounts for this. That's the permutation part of it, right? 5 combination, whoops, that's 5 permutation 2. But this 3 factorial, this divides by the number of arrangements of the 3 people you picked for that committee. So for instance, you could have person A, B, and C here, or you could have person A, C, and B, right? Or you could have person B, C, and A, or you could have person B, A, and C, A, B, A, and C, or you could have person C, B, A, or you could have C, A, B. If you're on a committee, all these 6 things are exactly the same. See that? The order does not matter. If it were a permutation, it matters what order you're in. So for that, you would divide by 3 factorial. What's 3 factorial? 6. That's why you divide by this 6. You get it? So 5 combination 3 is 5 times 4 times 3 divided by 3 factorial, which is 6, which comes out to be, let's see, 20, 60 divided by 6 is 10. Get it? Okay? So a combination is way less than a permutation because the order doesn't matter. It's just like pick a bunch of people, how many different ways could you pick those people? It doesn't matter who's president, vice president, or... Yeah, someone had a question? Yes, sir.
Aren't there 5 people?
Yeah. So,
Oh, does that continue?
what? No, we're done, right?
Isn't there like, if there's 5 people, wouldn't there be an A, B, C,
No,
and a
because
D?
only 3 people can be picked.
Good. So this is one instance, right? So if I chose person, if this is person A, right? So this accounts for all the different possibilities I could have, right? I could have A, B, C, D, or E, or here, right? Or F, A, B, C, D, or E. Then I could have 4 other things here, and then I could have 3 other people. But if I just chose A, B, and C, if that was one of my arrangements, I'd have to divide by the 6 different arrangements I could have of those 3 things. How many different ways could I get 3 of a kind? What time do we get out? 35. Okay, I got it. How many different ways could I get 3 of a kind? Well, now you have 4. So you have 4. If I'm playing cards, right? You want 5. Choose. It's 5 combination. How many are you picking? Oh, it's hard. 5 combination. It'd be 5 combination.
Why 5?
No, it'd be 52.
Yeah.
I think it's something like this. 52 combination
No, it
3.
should be
4.
Yeah, why wouldn't it be 13?
It'd be 4 combination 3, right? 4 different
No, every
So-
card is different.
times 13. That's how many different ways I could pick 3 of a kind. Because you have like 4 kings, right?
Yeah.
There's 4 combination 3 ways to pick 3 out of those. But then you multiply by 13 because there's 13 different denominations, ace through 1, ace through 2. Right? Is that 12 or 13?
Ace through.
13, right? So that's a different number of ways I could get different. You don't have to worry about that, but it's just kind of thinking. Hey, here's a good question. This is kind of an extension thing. What's the probability, how many people do we have in this class? 2, 3, 7, 11, not too many here, 13, 17, 21, 25, 20, 29 with me. What do you think the probability is? This is a probability problem, it's not a counting problem. Probability is the next section, but we're not going to do it. But what do you think the probability is that 2 people in this room would have the same birthday?
Is it like 60%?
Do you think it's really small or really big? Who thinks it's like less than 50%? It's actually like 60-something percent. You want to, we could check and see if it works, but I'll show you why. Because the way you'd figure that out, okay?
You use accounting, right?
Yeah.
The problem where you multiply the
I'll show you. You would do, so if there's 29 people in this room, there's 29 people in this room. How many, so the way you figure this out is you figure out, it's really hard to figure out the probability that people will have the same birthday, but it's easier to figure out the probability that people won't have the same birthday, okay? So if people don't have the same birthday, you don't want people to have the same birthday. What's the probability that people will not? So how many choices do I have for this person? How many choices do I have for her? 365, okay? So how many choices do I have for Sean's birthday if I don't want him to have the next birthday? Like 364, right? Until you get to all 29 people, right? So that would be, this isn't going to be on a test, but it's kind of interesting. 365 permutation 29. Do you understand that? That's the probability that everyone would have a not the probability, but the number of ways that everyone would have a different birthday.
We figure that out.
Out of the total possibilities, so say, how many choices do you have for your birthday? Say we're just pick 365. How many days could your birthday be on? 365, right? How many days could your birthday be on? Carmen, that's you. How many different days, choices do you have for your birthday? How many days in the year? 365. So what you have, the probability of no one having the same birthday
What if you have 2
would be 365 raised to the 29th power. So the probability is of no one having the same birthday is this permutation this divided by, it doesn't matter, right? 365 days, and you take that probability. So there's a probability of not having the same birthday. What would the probability that 2 people did have the same birthday? You subtract it from 1, right? Because the probability that it's going to rain is 20%. What's the probability that it's not going to rain? 80%. So that's the way you do it. You could do this on a calculator. Look, it's kind of cool. You could just go, where's my calculator? There it is. The permutation key is on your calculator. And so you're going to go 365 math. The PRB key is NPR is over there. 365 29, okay? Divided by, I think I have to do this in parentheses, divided by 365 raised to the 29th power. Okay? Did I do that right? Close the parentheses, hit enter. Okay? I put, delete. So the probability that no one would have the same birthday is 32%. Probability that we would have the same birthday is therefore what? 68%. Let's just do it really quick, okay? So so let's just pause for pause.